Okay, it's now my great pleasure to introduce our speaker today. Dr. Sean Andrew is an astrophysicist on the staff of the Smithsonian Institution Astrophysical Observatory, part of the Center for Astrophysics at Harvard University. He also a lecturer in the Harvard University Department of Astronomy. Before that, he was a Hubble Fellow at Smithsonian Astrophysical Observatory and a graduate student at the University of Hawaii. Dr. Andrew is a leading expert in the study of circumstellar disk and planet formation. He has authored more than 200 scientific articles during his career. And more recently, Dr. Andrew served as leading PI of the Disk Substructures at High Angular Resolution project, or D-SHARP in brief. That is an ALMA large program that image protoplanetary disk at very high angular resolution to study their small scale structure. So without further ado, it's my great pleasure now to turn the control to Dr. Andrews.
Okay, thank you. So I'm going to tell you today about what we're learning about small scale substructures in protoplanetary disks. And I'll start by explaining what I mean by that. So in the disk community, we talk about structure and what might that mean in this context. And unfortunately, like lots of areas of astrophysics, the meaning is sort of blossomed into many different things. But what I really mean, and I think what most people really mean, is the density distribution, the spatial distribution of the mass in the disk, be that in the gas or in the solid particles, right? It's often also taken to mean distribution of various other physical conditions or the material properties of the disks or so on. I'm showing here a little just schematic to orient you. Disks are not that complicated in the context in which I'm going to talk about. There's sort of two areas, right? There's the atmosphere, and then there's the midplane. And all the action we're going to talk about today is happening at the midplane where planets form, so on. And the midplane is primarily composed of gas and larger solids, which tend to settle towards the midplane, right? So the sort of fundamental tenet of disk research is that if you can actually measure the physical structure of the disk, you have some access to the quote unquote initial conditions available that you can use in planet formation models and sort of forward model what the outcomes might be of the planet formation process, right? Ultimately, you can compare those to what we see in the exoplanet population around much older stars, mature main sequence stars, and you can sort of iterate on that process to learn about the mechanisms that are relevant for planet formation, right? So the structures are sort of thought of typically as the initial conditions. And as we'll move along, you'll see that sort of simple quasi-deterministic view of the planet formation process is maybe in need of some revision. Because when we look at this at the disks in great detail, we see some confusing signals. So in the context of disk structures, there's sort of three fundamental challenges to planet formation. And you know, at least when I was in graduate school and being educated about the planet formation process, these were not actually problems. They were sort of glossed over. And the problems sort of start earlier than the classical problems in the core accretion planet formation process. And I'm going to talk about mostly two of these three things today, but they're all sort of related. And they're all sort of timescale issues, right? So the big problem, the fundamental problem, is that it's very difficult to keep solids in the same place in a disk for a long period of time, right? That migration creates all sorts of problems. So hanging onto the solids is an issue, right? I'll explain that in a little bit. The second issue, which is related, is that if you can't hang on to the solids, you often don't have the ability to concentrate them enough to make planetesimals, to create the building blocks of planetary cores or terrestrial planets, giant planet cores or terrestrial planets. And the third issue is that basically even once you have planetesimals and they can grow from collisions in the core accretion paradigm, it often takes a lot longer than we think we have available in the simple picture where planetesimals are growing by interactions with other planetesimals. So let me just explain why that's the initial problem is the retention of solids, right? So every planet formation model until recently sort of started with the classical picture of a protoplanetary disk, which is what we call smooth. Effectively, all that means is that you have relatively smooth gradients on large scales of key properties of the disk, the structure itself, right? So in this context, we're thinking the pressure of the gas decreases with radius, distance from the host star, right? So you can see my cursor, and this plot is just some model of a typical protoplanetary disk gas pressure. The reason that it decreases from the star is that the densities decrease as you get further from the star, and that's just gravity and how the disk forms. And the temperatures decrease as you get further from the star because the heating is dominated by stellar irradiation, right? So if you have a smooth gas disk where you have a negative pressure gradient as you move away from it, a negative radial pressure gradient, right? The force balance isn't quite the same as a standard Keplerian picture. If you take a little parcel of gas somewhere in this disk, you have gravity and rotation at some level balancing each other. But there's a little bit of an extra force from the radial pressure gradient, right? And that extra force sort of causes the gas to orbit at a slightly sub-Keplerian rate. So the gas is moving slightly slower than you'd expect it to move. The solids want to move on Keplerian orbits. And so what happens is for a certain range of particle sizes, those solids feel a drag force, like a headwind, and they lose angular momentum and they spiral in towards the host star, right? So that migration is called radial drift. And for certain particle sizes in the outer disk, we're talking tens of AU, those particle sizes are sort of like pebbles. And if you look at this plot, this is the radial velocity of those pebbles, where negative values are towards the star as a function of radius. Pebbles are moving actually quite quickly. About 100 AU, they're moving 10 AU per 1,000 years, or basically 10% decay in their orbit per orbital period. Right? Small particles are moving with the gas. They don't actually care what's going on. And very large particles don't actually care what's going on. So the sort of outcome of this is that you get this radial size segregation on short time scales, where you preferentially have larger solids near the star, smaller solids farther from the star, in that sense. So what happens is, on a very quick time scale, much, much shorter than the lifetime of the gas disk, all of the large solids have migrated into the inner 10 AU or so, right? And it's impossible to really form planetesimals at, say, Neptune's orbit or something like that. Right? So maybe those things just don't exist, or maybe there's a fundamental problem in the assumption of a smooth gas disk, right? So this migration problem, this radial drift problem, was sort of discovered in the 70s, and at the same time, the potential solution to it was mentioned, right? And that is that you just don't have a smooth gas disk. So I've taken that same gas disk and I've perturbed it with just a sinusoid of low amplitude, right? So you can see it over here in this plot. I've changed the density by 10% or so in a sinusoidal variation. This is from Paula Panilla's PhD thesis. And then you evolve the gas and dust in the same way, right? So what happens is that basically you get this convergent migration to the peaks in the pressure, right? So what happens is that you're in the same scenario outside of a local peak. You're in the same scenario you were in before. You have a negative pressure gradient that causes the gas to move at sub-Keplerian speeds, and the particles migrate inwards towards the peak. Just interior to the peak, the opposite happens. The gas is moving at super Keplerian speeds, and it sort of accelerates particles out into the peak, right? It's the exact same physical process, but the solids will move to the local peak in the pressure, right? So you can see that in this velocity plot, but the more important one is this density plot. Surface density is a function of radius. So what happens is the larger particles that feel this pressure perturbation, that are affected by this pressure perturbations more strongly, they become very concentrated locally, right? So if I'm going to go back just one slide to show you an important difference, right? If you look at the solid, the centimeter sized particle density is if you divide it by the gas, right? You're down by orders of magnitude, 3 orders of magnitude. You concentrate the particles, you're getting up towards unity. The solid ratio, the solid to gas ratio heads towards unity. And so this solves sort of all of our big problems in principle, right? Like you're retaining the solids because you're effectively trapping them at local pressure perturbations. If you can trap them, the solids to gas ratio goes up very high. And then you're able to in principle, form planetesimals through a direct hydrodynamical collapse or gravitational instability because you have a feedback reaction from the solids into the gas, right? So that solves 2 of our 3 problems in planet formation models. And the third problem is basically if you can actually form planetesimals very quickly at essentially any location where you have a gas pressure perturbation, then you have a seed particle to grow a giant planet core. And the sort of big change in the core accretion model over the past 10 years has been that the idea that you can basically capture lots of pebbles to grow that core very quickly. It's called pebble accretion. So if you form planetesimals in these pressure peaks and then you have this stream of small particles coming into the pressure peaks, you could potentially form a planetary core very rapidly, right? So that's all great, but this is a toy, right? This model that I'm showing you is a toy. I've just multiplied by a sinusoidal function. The question is basically, do these small scale perturbations to the gas pressure distribution really exist in reality, right? So we'd like to try and find them, and finding them is actually not trivial, right? So this is where the term substructure comes from, as you might imagine. I told you structure was the density distribution, and substructures are small-scale perturbations to the density distribution. So in order to find these things, we think we need very high resolution. I can tell you, you do need very high resolution. And the reason is that you expect that the gas pressure perturbations are really only stable when they're at sizes of about the pressure scale height, the gas pressure scale height. And for typical disk temperatures, we think that's of order 5 or 10% of the distance from the star. So if I stick some numbers in there, you can see that pressure perturbations at a radius in the disk of 1 AU can be expected pressure perturbations of the scale of 1 AU can be expected at a disk radius of about 10 AU. So that's 7 milliarcsecond resolution for typical star-forming regions. The number's more like 5 AU at about 50 AU, right? So you also need good sensitivity. You need sort of pressure amplitudes, pressure differential amplitudes of about 10% minimum to be able to start trapping solids. The good thing is that if you try and observe these perturbations, you're going to try and observe them using a diagnostic of the particles that are being trapped. And if the particles that are preferentially being trapped are pebbles, millimeter, centimeter size things, you're going to be looking at the millimeter, centimeter continuum. And since those particles are amplified in the traps, the density perturbations are much larger, even small gas pressure perturbations can be seen in principle in the thermal emission from those small particles in the millimeter continuum, right? So sensitivity is important, but it's not the key important thing. It really is resolution that makes this difficult, right? So starting about 5 years ago, we had some new opportunities using the long baselines with ALMA. So I'm showing you these are not blurred images. These were the best we had, the best spatial resolution images of disks that we had. I guess this is 8 or 9 years ago, right? With the precursors to ALMA, KARMA, and the submillimeter array. So these are 2 disks, and they're sort of observed at 20, 25 AU resolution. And I can tell you that we did a lot of great science with this kind of resolution images. But when ALMA gave access to their 15-kilometer baselines for the first time, this is the kind of thing that we saw, right? There's a huge dramatic difference in the inferred structure and substructure of these disks. Right? So the disk on the left is the famous HL tau, which was observed as part of the campaign to test and calibrate long baseline data by ALMA. And I would say at some level it was sort of serendipitous. We hoped we'd see some interesting things, but we didn't really know what to expect. On the right is the image of TW Hydra that we observed the following fall. That was expressly sort of proposed because we didn't think that there was any way that this disk could survive so long without having these substructures in it. Okay, so we know that when we have access to something like 30 milliarc-second resolution, we're going to be able to start seeing substructures in protoplanetary disks. So we proposed, as Andrea mentioned in the introduction, we proposed to do a large program to look at a lot of these disks. And that was this D-Sharp program that I led with Andrea and Laura Perez and Kees Dillemond. So this is a gallery of the D-Sharp disks, and they're actually shown here to physical scale. So you have quite a range of sizes and structures. And basically what happens is you see substructures in all cases. There's a remarkable diversity and variety of things that you do see. I'm going to go through a few of them quickly. So one thing that we learned is that these small substructures, few AU substructures, are ubiquitous. And they're most often concentric rings and gaps, as you see in these images. And those features can be found anywhere in the disk, all the way out to the edge of where you see continuum emission. And there doesn't seem to be any real connection to the host stars, as we've seen now in a number of studies with different samples. Most of those gaps are actually narrow and unresolved, even with D-Sharp, even with the best ALMA resolution we've been getting, smaller than 5 AU. And the depletions could be, a few percent to more than a factor of 100. It's a little bit hard to tell if they're in the cases where they're unresolved. You only have a lower limit. We don't see a lot of azimuthal asymmetries. They're there in some cases, as you can see in these really sort of spectacular examples where you see these little arcs in these disks by Laura Perez and Andrea Sella. They're a little more prevalent in a different kind of disk called transition disks, and it's not clear if there's some selection effect happening. In my mind, the most interesting or the most surprising thing to me is the finding of these complex spiral patterns in small subsample of these disks. And that is where you see, these are polar projections of these images, where you see these spiral arms crossing sort of diagonal patterns, right? And the most interesting thing is that the arms, it's a little easier to see in this case, the arms cross these concentric, circularly symmetric gaps in the disks as well. I don't really know what that means, but it's really interesting in terms of the potential mechanisms that could create it. I'm actually not going to talk about the mechanisms. Feel free to ask me about them that have been proposed. There are too many of them, frankly. But what did we learn about the origins of these substructures? I think just empirically, we can say a few things. One is that basically the prevalence tells you that alone tells you that there's some universal set of processes that generate substructures in disks. This is a common phenomenon, and it might even be ubiquitous. And whatever is causing the associated perturbations to the disk structure usually requires a significant degree of symmetry. And the ring widths, the sizes of the substructures are narrow. They're at the scale of the pressure scale height, or even smaller in the continuum, and they imply traps at local pressure maximum. So the question we always get asked is, are these actually young planetary systems causing these perturbations? And this is a good question. I'm not going to say yes or no, but you can actually create these substructures, even complicated cases like you see here in the observations where you see many, many rings. Here's a hydrodynamic simulation where actually you could produce all those substructures with one single planet located in this large gap, right? So it's compelling, and it's not actually that difficult to explain the observations in this way. If you look at this plot over here, if you estimate the masses that you would find to be able to produce the substructures like we see and their locations, they're sort of an interesting complementary part of parameter space compared to the standard exoplanet surveys that we do now. So there's a lot of fruitful potential avenues for research in this direction. So I want to say a few things about where the field is going. I think I'll sort of split it into the near term and the further term, right? It's still pretty early days. And one of the big issues that's of interest to all of us is basically to learn more about the demographics of substructures. T-Sharp was great, and there's a few other samples out there. Fun Long and Mika van der Marle have done nice surveys as well. But the samples are sort of necessarily biased. I shouldn't even say necessarily, at least in the D-Sharp case, it was biased by design. If you actually want to resolve and see substructures, you have to look at them in the outer parts of the disk, where the pressure scale height is larger and comparable to the resolution of ALMA. And so by definition, then you're observing the brighter, bigger disks, as you can see in this diagram here, sort of preferentially observing things that are sort of more characteristic of solar mass hosts for their stars, whereas most of the rest of these things are lower mass stars where there's a lot more of those objects. So probing the substructures in this population, the sort of more common faint small disk, will be hard and in some sense inconclusive because you're only accessing the largest substructures until you have much higher resolution, like is possible with the NGVLA. The best bet in terms of understanding demographics now, I think, is to try and look at samples with different ages or different evolutionary states to see how they might, when they might form and how they might evolve. So another real growth area, I think, in the last couple of years is to be looking at quantitative complementary data sets, right? And really, in my mind, this is looking at substructures in the gas phase directly, right? Things can look very different. This is an observation of one of the D-Sharp sources where just in this white little patch, you see perfectly symmetric rings. And in the CO, you see this enormous spiral pattern by my recently graduated student, Jane Huang. If you look in detail at the kinematics, here's a channel map of CO from one of these disks, and you see this perturbation right here that's associated with the gap in the dust, right? So you can look for kinematic perturbations. And this is a study by Rich Teague where he sees not only kinematic perturbations, but brightness temperature perturbations that look sort of spiralish in nature, right? So there's a lot of interesting stuff you can do with spectral line observations from ALMA, basically tracing out the 3D behavior of substructures. You can also do this in some sense with reflected light from small grains using infrared, high resolution infrared observations. And the really nice thing is that from kinematic features, in principle, you can measure pressure perturbations without relying on the intensities. And of course, we're all pushing towards a future where we have access to sort of a different window on the spectrum at longer wavelengths, and that's with the NGVLA. So the NGVLA, in my mind, provides two key advantages. One is that you are observing the lower frequency continuum. So that gives you access to much lower optical depths. So you could potentially see asymmetric substructures, for example, that are masked because of the higher optical depths of the ALMA wavelengths. And it gives you access to larger solids that you don't have access to in the millimeter. And those two things are basically crucial if we ever want to quantify trapping of the particles and learn about how the environment in which planetesimals might be formed. But really, it's sort of the thing about NGVLA that's so interesting to us that are studying substructures is the access to very high resolution, where we can actually, the combination of that and the lower optical depths will allow us to see substructures inside a few AU for the first time. And I'm showing here some in-prep simulations from Harder and Ricci and their team of basically NGVLA simulations at 3 millimeters, 7 millimeters, and 10 millimeters of 1 in 10 Earth mass planets at 3 AU and what they might actually look like. So these are really sort of pushing the boundaries of NGVLA, but it's a really interesting future in the inner disk. So I'm going to just put up a last slide just to remind you that substructures are really fundamental pieces of the planet formation puzzle. In a sense that disks might actually be nothing but substructures. And so studying them at very high resolution is sort of the key to understanding all of properties. And here's a few resources if you're interested in learning more. There's a annual reviews article that covers this and other topics that is on the archive now. The D# articles were published in an AppJ Letters focus issue and at the very end of 2018. And more importantly, if you don't know, you can get all of our calibrated data and scripts and data products online from the ALMA website. Please use them. And there's also some great articles by Ritchie et al. And van der Marel et al. In the NGVLA science book, myself as well, about various aspects of substructures and particle trapping and what the NGVLA will be able to do in the future. So thanks very much.
Thank you, Sean, for the very nice talk. And we already have a few questions for you. So if you go back to your D# image gallery, one of our attendees is asking whether the second image on the top row is a binary. So there are binaries. Can you say something about what we have learned about binary systems?
Yes, I wonder if this was a plant. Thank you for asking, because I didn't have time to really get into it. So in the D# sample, we didn't expressly avoid binaries. Binaries were sort of down selected by their nature because they tend to be fainter because of dynamical truncation of their interactions. But 2 binary systems actually made it into the sample, and we just let them be there. Sorry. I'm trying to move my little gallery out of the way. So the one here in the top left, second from top left, is indeed a binary. It's in fact a triple system. The third star is, you know, up and to the right off your screen. And indeed, we do see disks around both components. And then if you go 1, 2, the third and fourth over from that, those are actually separate components, again, of a triple system. This little ring system has 2 stars at the very center, and this is the sort of tertiary, about 100 AU away. And what we see in those cases, and in other cases now, of binaries, is the primary disk is usually bigger, and the primary disk usually exhibits very tight spiral arms. This is basically what you would expect from hydrodynamic simulations of these tidal interactions. And yeah, so there's a big fruitful area there to learn more, to do more sort of hydrodynamic simulations where you have access to this information. There's lots of great CO data as well for these sources. Yeah, it's a good question. Thank you.
Okay. Another question goes in a place where maybe you don't want to go, which is what is the most promising observational technique to better understand the origins of this structure? And I add to that, so what is your take on the possible origins of these structures?
Right, so, I mean, in my mind, the origins sort of boil down into 2 categories, and this is like a very non-theoretical point of view. But, you know, there's sort of, the 2 origins are sort of, there are fluid dynamics arguments that produce these things naturally without any perturbers. And there are a lot of different instabilities that we think could occur in these disks and produce substructures like we actually see. So in that sense, I sort of think of those, I think of that picture as sort of these disks really are, in a sense, protoplanetary. And the various hydrodynamical instabilities or fluid mechanical properties of the disks are sort of organizing the structure in a way that promotes the formation of planetesimals and then later of a planetary system, right? And then there's sort of the opposite perspective, which is basically that these things are not protoplanetary, but they're sort of recently post-planetary, and you're forming all these substructures by perturbations from a young planetary system, right? And that seems a little circular in a sense, but I think, you know, it just sort of suggests that if the story that we're all telling ourselves is true, then that actually just means that this is probably not the first generation of substructures, right? And you probably had something to create the planetesimals very early, and you actually make planets very efficiently at very young ages, right? So that's sort of especially exciting for that that reason as well, not just the potential of finding very young planets. So differentiating between them is tough. I think, on its face. There are certainly examples, I would say, that point in a promising way towards planet-disk interactions. The disk PDS-70, of course, as Andrea knows, is probably the most compelling case where you actually see some perturbers in a much more strongly perturbed disk than I'm showing here. And I think, like, the real path to that, to understanding things better is probably in trying to quantify the pressure perturbations, right? So, like, in an ideal world, in the immediate future, what you want is deep, high-resolution molecular line observations of these disks. If you can actually see perturbations in optically thin emission lines, right? Optically thin line emission is basically proportional to pressure. So if you can measure the amplitude difference there, you're measuring the pressure. And if you use the kinematics, you have an independent measurement of the pressure perturbation. And then I think you can sort of start to test the theoretical ideas that are going around. And, at some level, the computational stuff is really getting going. And as the computational power increases, it'll be easier to make sort of direct quantitative predictions about what you expect to see in different tracers. And that's starting now, but I think, like there's still a lot of quantitative work to do there.
Related to that, the second part of the question was, is JWST going to be helpful to better constrain different disk populations?
So, I mean, in one very obvious way, in some cases, JWST might be really groundbreaking for this purpose, right? So obviously, JWST is probably the most sensitive instrument to circumplanetary disk material and or young planet atmospheres. Right. So you'd love to look in one of these gaps with JWST at high resolution and look for point sources, right? That's the smoking gun if you have a planetary perturber. Now the downside is that JWST's occulters, their coronagraphs are quite big compared to the locations of these gaps. So there's actually just a small subsample of these that are sort of easily amenable to that process, but obviously that would be pretty groundbreaking. I think, otherwise JWST is sort of giving us, decent imaging in the mid-infrared scattered light. There are some good facilities on the ground now that probably can do just as well, if not better. It's not really sort of a high resolution, spatial resolution instrument for protoplanetary disks. I think the situation is quite different for nearby debris disks, where you have access to the debris belts at very high resolution because they're much closer to the Earth. So yeah, it'll be interesting, especially in the very beginning, I think, because you'll get these great searches for young planets in the sort of handful of great examples, and really start to learn something about whether or not those things are opened by planets.
Okay, we have a couple of other questions that go back a little bit to the origin, maybe. One is, are there any sign of bars at the center of protoplanetary disks?
So let me go to the spirals. So, I mean, I would say that there's nothing really definitive in terms of a bar. But I don't know that we actually have the ability to see that kind of thing because the very inner parts of these disks, the optical depths are quite high, right? So you sort of lose that contrast. Remember, when you see a bar in a spiral galaxy, you're seeing it in starlight or not, right? Here we're just sort of ramping up the optical depth and it becomes very hard to see. It would be interesting to try these things at lower optical depths, right, within GVLA, and look for those kinds of dynamical signatures that could tell you something about what's happening. If the questioner is getting at whether or not this is a sort of tomb ray instability type scenario like you might see in some spiral galaxies, I think there have been a host of papers about this since this spirals article from D Sharp came out. And I've seen the full gamut, even I think from some of the same people that know they're not commensurate with gravitational instability to think even last week there was a paper saying if you treat the dust dynamics, they could very well be commensurate with gravitational instability. So I think that's really interesting, and there's just a lot of work to do there. So, but yeah, I would say that there's no, in my mind, there's no obvious bar signature. We do think that the arms are trailing arms, given the rotation of the gas, but that's about all we know.
Yeah, so related to that, and to some extent you already have answered to that. So one other question is, what are the leading ideas for creating spiral patterns in gas, given that they are not easily explained with planet models, planet interaction models?
Well, I mean, I think, planet interaction models are indeed a potential explanation for these sort of m=2 spirals that we see, right? And usually that's thought that the perturber is in the exterior of the spiral pattern. And it would have to be a relatively massive perturber, like a few Jupiter masses or more. And certainly we actually do see, this connection between spiral patterns in the disks when you have a much higher mass ratio perturber in the binaries, right? In these three cases, and in the few others where you see this this pattern, at least in the millimeter, there's no detectable perturbers to my knowledge, right? And it's sort of flirting with tension there with that idea, because AO observations from the ground should be sensitive to those kind of planetary perturbers. There's all sorts of ways to weasel out of that, but anyways, a real perturber could cause it. And it doesn't necessarily have to be in orbit either. It could have been a flyby perturber. I think the statistics is again problematic there, because you wouldn't expect so many things to have flyby perturbers necessarily. But yeah, usually for the millimeter, those are the ideas: is a perturber, perhaps with some eccentricity to its orbit, or a global gravitational style instability. Pictures can be slightly different if you see it in scattered light, where you're seeing up in the atmosphere. But I think for the millimeter continuum, those are probably the options. Neither of them really seem to work on their face either, I should say, but compared to the observations. But I think there's still more parameter space to explore there. Okay,
fantastic. I have to say that we are receiving more questions than what you would probably be able to answer. So I'm gonna filter a little bit through that. I would like to move a second. We have two kind of technical questions, and then if we have time, go back to the science. One of our attendees pointing out that the ALMA band 1 receiver, which will be working 1 centimeter, will begin installation soon. And studies are exploring increasing baseline length, very possible at this low frequency. And so, do you want to comment about what ALMA could do, maybe compared to the NGVLA, once this centimeter receiver will be available? And what kind of baseline will we need?
Right. So, if you want to be comparable to the D-sharp images, right, you need sort of 5 times longer baselines. So you need sort of 60, 70 kilometer baselines to get the same resolution. I do think, just collecting area wise, you'll have a pretty serious sensitivity problem. Like, I mean, it'll be doable, but it'll be a pretty big investment of ALMA time per source. And that I'm saying that assuming that the optical depths will be low at 7 millimeters, right? I think, it's not clear that, if the optical depths at 1 millimeter are sort of, 1 to 10 or something like that, then sensitivity will be difficult with ALMA at these very high resolutions. I think, if it's still optically thick, that helps you in some sense. But I think, like the key about the longer wavelengths for this particular science is leveraging that lower optical depths to probe the inner part of the disk. And to do that, you need much higher resolution, right? I think you start putting ALMA antennas in different countries if you do that, which maybe no one really wants to do. But I think it would be a bit difficult. That really specifically, those lower frequencies are sort of much better suited to a project like NGVLA.
I think you have to build the NGVLA around
stuff you could do in band. There's all sorts of stuff you could do in band 1 with ALMA, but this particular thing would be a challenge.
Right. I have another technical question that maybe is interest only for a few of us, but I think it's actually rather important, which is, so one of the questions is, for measuring the details of the extended structure, such as peak to valley ratio, how robust are those with ALMA limited, and limited is in quote, UV spacing? Or another way of asking is, does the usual way of image deconvolution using clean works, or what kind of tweaking? Or at the end, I mean, and I'll add, so we always show images, but that's not what an interferometer actually measures. So how reliable how robust are these images against the deconvolution techniques?
Yeah, I mean, that's a good question. So there's sort of layers to that, right? Like, obviously these images I'm showing you were generated with multi-scale clean. We did in D Sharp, at least, we did experiment with the imaging algorithms that were used by the EHT team for their, at the same time they were developing the imaging algorithms for all the M87 black hole images. That was all happening down my hallway. And so we sort of exchanged visibilities and applied our own imaging algorithms. So there actually wasn't any qualitative difference in those examples. Although I have to say, like now there's sort of, there's a bunch of different options that people are floating around and using them for protoplanetary disks, and you can push the resolution at some level, I think, without as much penalty as you would a normal clean, and that's great. But I think, as Andrea said, usually, so I've sort of been kind of careful to not give you quantitative numbers on a quantitative assessment of those things, because normally in the disk community, we would do this, and I think the right way of doing it is actually modeling the visibility data directly. So you avoid these issues. The images are sort of a guide, and then you would use the visibility data to extract quantitative information. And in some cases people have done that, and some of this data is still ready to be done. And if you want to try and push it and measure things in the visibilities, that's why we made the data available. So please go ahead and do it. I would say that it's sort of it becomes a pretty complicated problem to deal with. But I'm excited to play around with. We have a bunch of different algorithms we're playing around with for basically regularized maximum likelihood imaging. I think have good promise for ALMA data like these.
Cool. Okay, I think we have time for a few more questions. So I'd like to go back to the scientific topic of your talk. One question is about the distribution of material in the outer part of the disk. In particular, say pre-ALMA conclusion about protoplanetary disk, where that they have exponential density profile at the outer edges. Does this conclusion hold up in the much higher resolution ALMA data?
So yeah, in a sense, I think that's true. I mean, all right, so there's sort of two layers to that as well. Like in the gas, that seems to be true. Like there's sort of an exponential distribution of gas. It extends out significantly further. But even in the continuum, if I were to plot, well, unfortunately you can't see it in this plot. I'm trying to see again around my little thing. You can start to see it in this example when you get out to 120 AU or something like that. The profile just turns over, and you could draw sort of a double power law type behavior on here. So I think sort of in general that's true. Like the outer disk sort of cuts off very steeply. It's not clear if it's exponential or if it's just r to the -8 or something like that, but that's generally true as far as we can tell. Measuring the density profile actually in a gas tracer is of course really difficult, right? So, you know, if you want to try and observe the cold stuff far away from the star, you have to look at an optically thick tracer like 12CO, and then you don't have access to density information really. You try and look at an optically thin tracer, and then you're trying to differentiate between, you know, the chemical abundance inventory and the density profiles. But it does seem like there is a low density distribution extending to much larger radii, at least in the gas.
Okay, great. So we have a few more questions about the substructure now, and then I think we are ready to wrap up here. So one question is, how stable are substructure likely to be to changes that might be caused by Fu Orionis outburst or to other less extreme accretion instabilities? So do you think there may be, or both in terms of stability or connection between accretion events and substructure?
Yeah, that's a good question. So thinking particularly at substructures at earlier phases of evolution than I've shown you here, right? So in all the disks that we're observing in D sharp and a lot of these substructures in many cases have been sort of safely in a low accretion state for a long time. But obviously there's a big push to look at what's happening at earlier times where you do have these powerful outbursts. And at face value, an outburst basically will change the thermal structure of the disk, even at large radii at some level. You change the thermal structure, you change the pressure structure. So I don't know that it would actually be in the scenario where you'd sort of necessarily completely destroy what's going on at the midplane. But certainly you can imagine that on the scale of that you have outbursts, you could change the distribution of particle traps as a function of radius, right? For some brief interval. I think it really just depends on how strong the outburst is in their cadence and so on. But that is a really interesting prospect. I think a lot of the interesting stuff's going to be happening in the quasi-embedded phase, where those are a bigger issue. I think, normal, low accretion states here where you have accretion rates of maybe 10 to the minus 8 solar masses per year or something like that. I think we'll have certainly these outer parts of the disk that we're able to observe with ALMA will have almost no effect on things. Certainly the level of viscous diffusion in the disk that might be created by whatever mechanism is driving the accretion process, that certainly matters, but not the actual sort of mechanical work of the accretion process itself in these scenarios. I think, you start pushing inside 1AU with NGVLA, then you need to start worrying about these things a lot more, right? Because you're a lot more affected by what's going on at the stellar boundary.
Okay, so we have a few questions about spirals again. Clearly spirals are kind of intriguing. So one question is, how many systems are known with spiral arms in the millimeter continuum, but they show no arm in scattered light, or vice versa?
Oh, that's a good question. So at some level, that's sort of subjective, right? So like, so let's take these three examples, right? So this one here is IM loop, which actually has an enormous scattered light disk with a very strong amount of flaring. And if you look at that, these are VLT sphere observations. I first saw this in Havenhouse's data, but I think there might be more data sets. And there are signs of substructures if you look into the flared surface in the inner parts that look sort of like rings, but they could very well just be the tightly wound part of spirals in here. So I think in that particular case, the geometry sort of makes it hard to tell what's going on. In these two cases, this is WALV6 and this is Elias 27. To my knowledge, actually, Elias 27 does not have a good scattered light measurement because it's deep in the OF clouds and its optical magnitudes are very low. WALV6, I think, does have a scattered light measurement, and I don't believe it shows spirals, but I think, it's not necessarily that there aren't spirals there. It just might be that they're, it's not the best, your ability to measure the polarized scattered light is maybe not the best. So I think there's a lot more examples of the cases where you see spirals in the scattered light and you don't necessarily see spirals in the millimeter. And that actually could be all sorts of things. It could, again, be a resolution problem, or it could actually be related to the mechanism that you're actually seeing. But it's, there are theoretical predictions. It's a little easier to see spirals up in the atmosphere where it's warmer, so opening angles are different than in the midplane. But I think, this is still a big open thing. Connecting the millimeter continuum in the infrared scattered light, I think we're sort of just getting started there on more than a few individual sources. So I think there'll be a lot to learn there. But yeah, I'm struggling to think of examples and counterexamples, but there's nothing obvious in my mind.
So related to this, it could be related or not. One of the listeners asked, what is the fraction of disks that have been observed with ALMA that show evidence for warping in both millimeter and optical? Some of the disks with spiral also have warping, right?
Yeah.
So do you know what is the fraction of disks that actually show warping?
That show warping in the millimeter continuum. I don't know of any obvious examples of warping in the millimeter continuum.
Or in the infrared, or in there is some warping molecular gas, for example.
Yeah, there's some evidence of warps, or I guess, they can be interpreted, I suppose, in different ways. But yes, line of sight velocity deviations that are consistent with warps for sure in some cases. I think you see those, and perhaps it's just easier to see them for various technical reasons in the transition disks, where you see primarily most of the continuum is in one narrow ring, and then you have a much more distributed gas disk. Yeah, I don't know off the top of my head, I don't know the fractions, but certainly the perturbations in the vertical dimension is an interesting avenue that's obviously best explored in complement with scattered light and molecular line images.
So again, on spiral, we see spiral structure in binary systems. So one of the listeners asked whether simulation have been done to see if this structure just compatible with the binary, so dynamic interaction between two objects.
Yeah, I mean, I think that's the, certainly, so doing a bespoke model of an individual system where you don't really have the 3D geometry and impact parameter of the orbit. You don't even know the orbits of the stars. You just know that they're physically associated with one another. That's tough. But even still, there are really compelling hydrodynamic simulations that look very much like the observations in a qualitative sense. So it's sort of the same picture as in galaxy merger simulations, where you can't measure the orbital period of a galaxy merger or something, but you can sort of start to tweak your hydrodynamic simulations to learn about the merger process. I think at some level that's where we're at with these things. But indeed, you can make these kinds of spiral patterns, particularly in the gas, through dynamical interactions with the perturber. And I'm trying to think of is it HD 100546 that has an M-star perturber and a nice spiral pattern, and there are some really nice simulations of that. I'm sorry that I'm blanking on who did that study, but indeed that is the case.
Okay, I would like to conclude with a question which is always related to spirals, and a kind of more speculative and opens up to other explanation. And the question is, dark matter perturbers. Could one model the distribution of dark matter from known example of spiral pattern of this? I have colleagues, for example, that talk about clumpy dark matter model and how you could constrain that based, for example, also on the distribution structure of protoplanetary disks. So do you have any thought about that?
No. I mean, in principle, since we can't see any perturbers at all, I don't see it. I mean, gravitationally, I don't see why it would be any different, right? Like in principle, you could develop models for clumpy structure that would have to be sort of, distributed at sort of Jupiter mass level things. But yeah, I not thought about that at all.
Okay, thank you very much, Sean, for the talk and your availability to answer to all these questions. And I think we should stop here. We are almost at the end of the hour. So I would like to thank again the speaker and all the participants. And I hope you'll join back the next talk next week. So have a good day.
Thank you.